Alright, so today we are building something actually useful. A file encryption app with a drag and drop UI. You drop a file in, it gets logged with a password. Nobody can open it without that password. Not even you if you forget it. So let's get into it. First, we are gonna create a folder called Personal File Locker. Right click on it and click on Open in Terminal. Then write code dot. It will open your folder in VS Code. Open your VS Code terminal by Ctrl plus tilde and create a virtual environment by this. Now we have to activate that virtual environment. So write as you can see, it has been activated. Now, create main.py file and download these packages. We import OS to work with files and check things like whether a file exists. We import time so we can track things like failed login attempts and lockout timing. We import HMAC to create secure message authentication codes that verify encrypted data integrity. We import hashlib to generate secure hashes like SHA-256 for password verification. We import tkinter as tk to build a graphical user interface for our application. From tkinter we import message box and simple dialog to show pop-ups and ask the user for passwords. We import tkinter dnd and dnd files from tkinter dnd2 to enable drag and drop file support in the GUI. From crypto.cipher we import AES, which is the encryption algorithm used to secure files. From crypto.protocol.kdf we import pbkdf2 to derive strong encryption keys from user passwords. We import getRandomBytes to generate secure random values like salts for encryption. Finally, we import pad and unpad to correctly format data so it fits AES encryption block sizes. We set salt size is equal to 16, which defines a 16-byte random salt used when generating secure encryption keys. We set key size is equal to 32, so AES encryption uses a 256-bit key for strong security. We define iterations is equal to 1 lakh, which makes pbkdf to run many rounds to slow down brute force attacks. We store AES.block size in block size because AES encryption works in fixed size blocks. We set HMAC key size is equal to 32 to generate a separate secure key for verifying data integrity. We define max attempts is equal to 5 to limit how many times someone can try unlocking a file. We set lockout time is equal to 30. So after too many wrong attempts, the user must wait for 30 seconds. We create failed attempts, which is a dictionary used to track incorrect password attempts per file. Finally, masterfile is equal to masterfile.log shows the file name where the master password hash will be saved. Now I'm gonna add theme colors and fonts. You can copy it. I have provided GitHub project link in the description. We create the main application window using tkinter.dnd.tk so our GUI supports drag and drop functionality. We set the window title using .title so the app appears as Advanced Image Vault in the window bar. We define the window size with .geometry 560 by 360 to keep the interface compact and clean. We disable resizing using .resizable, false and false, so users cannot stretch the GUI layout. We apply the main background color using .configure to match our dark theme. Now we create a frame called container using tk.frame to hold all the GUI elements inside the main window. We place this frame using .pack expand true so it stays centered and expands nicely within the window. Then we create a label using tk.label to display the main title Secure Image Vault at the top of the interface. Finally, we display the title on the screen using .pack padding is equal to 30 and 10, which adds spacing above and below the title for better layout. Here we create another label using tk.label called subtitle to display a short instruction telling the user they can drag and drop files to encrypt or decrypt them. We place this subtitle on the screen using .pack so it appears right below the main title. Next, we create the drop area label using tk.label, which acts as the visual box where users will drag and drop their files. We set properties like width, height, bg, fg and relief is equal to ridge to style the drop area and make it look like an interactive drop zone. Finally, we display this drop area using .pack pad_y is equal to 30, which adds vertical spacing so the box sits nicely in the center of the interface. We call .drop target register DND files, so the drop area can accept files dragged into the application. We then use .dnd bind, drop, handle drop to connect the drop event with the handle drop function that will process the dropped files. Next, we create a status label using tk.label, which will display a message like ready, file logged, or file unlocked to keep the user informed. We display this label using .pack pad to add some spacing and keep the layout clean. Finally, we run setup master to ensure the master password is created or verified before the app is used. Then root.main loop starts the tk-enter event loop which keeps the GUI running and responsive to user actions. This setup master function is responsible for creating or verifying the master password before the user can access the vault. First, we call root.withdraw to temporarily hide the main window while the password setup or login dialog is shown. Then we check os.path.exist master file to see if a master password file already exists on the system. If the file does not exist, we use simple dialog.askString to ask the user to create a new master password securely with hidden input. If the user cancels or leaves it empty, we immediately exit the program to prevent running without protection. Next, we open the master file using open and we're gonna write in binary so WP and store a SHA-256 hash of the password using hashlib.sha256 so the real password is never saved. After saving it, we show a confirmation pop-up using messagebox.showinfo to tell the user the master password was created successfully. If the master file already exists, we again use simple dialog.askString to ask the user to enter the master password. We then open the file using open and we are gonna read in binary, so RB, and read the stored password hash. Next, we hash the entered password again using hashlib.sha256 and compare it with the stored value to verify authentication. If the hashes do not match, we show an error using messagebox.showError and immediately terminate the program. Finally, if everything is correct, we call root.deiconify to show the main application window again so the user can use the vault. We create drop queue, which is a list that stores all the files the user drops into the application. Next, we define the handle drop function, which runs whenever user drops files into the drop area. Inside the function, we declare global drop queue, so we can modify the queue from inside the function. Then we use root.tk.splitlist event.data to convert the drop file data into a proper Python list and add it to our queue using .extend. Finally, we check if the queue was previously empty, and if it was, we call process next file to start handling the drop files one by one. This process next file function processes files from the drag and drop queue one by one and asks the user whether to lock or unlock them. First, we check if not drop queue and return immediately if there are no files left to process. Then we take the first file from the queue using dropqueue.pop so files are handled sequentially. We verify the path using os.path.isFile to make sure the dropped item is actually a valid file. If it is not valid, we simply call process next file again to skip it and move to the next one. Next, we create a pop-up window using tk.toplabel, which will ask the user what action they want to perform. We customize this window using .title, .configure, .geometry, and .resizable to give it a clean, fixed layout. Then we call .grabset, so the user must interact with this window before going back to the main interface. We create a tk.label showing os.path.basename and file, so the pop-up displays the name of the file being processed. Then we create a frame using tk.frame called btnFrame, which will hold the action buttons. Next, we define a small helper function, close window and continue, that runs the selected action, closes the pop-up and schedules the next file using root.after. Finally, we create two buttons using tk.button inside the frame. One lock button that calls the lock action through a lambda and one unlock button that calls unlock action. Each button is displayed using .pack with side positioning and padding so they appear neatly next to each other. This lock action function is responsible for encrypting a file when the user chooses the lock option. First, we check is locked to make sure the file is not already encrypted. If it is locked, we update the UI using statuslabel.config and show a warning pop-up with messagebox.showWarning, then stop the function. Next, we ask the user to enter a password using simple dialog.askString with hidden input. If the user cancels or leaves it empty, we simply return to avoid encrypting without a password. Then we call encrypt file and give file path and password, which performs the actual AES encryption on the file. After encryption, we update the interface using statuslabel.config to show success and confirm it with messagebox.showInfo. This is locked function checks if a file is already encrypted. It tries to open the file in binary mode and reads the first 6 bytes. If those bytes equal binary locked, it returns true, meaning the file is locked. If there is any error, like the file doesn't exist, it safely returns false. This encrypt file function handles encrypting a file securely using a password. First, we open the file in binary mode and read all its data into memory using f.read. We generate a random salt with get random bytes, which ensures each file has a unique key even if the same password is used. We derive two keys using pbkdf2, one for AES encryption and one for HMAC to verify the file hasn't been tampered with. We create an AES cipher in CBC mode and encrypt the padded data using cipher.encrypt. The HMAC tag is calculated with hmac.new, so we can later check if the file content is unchanged before decryption. This adds an extra layer of security to detect any corruption or modification. Finally, we overwrite the original file with the binary locked marker, the salt, IV, HMAC tag, and the encrypted ciphertext. This format allows our program to recognize locked files and recover them safely when the correct password is provided. By combining AES encryption with HMAC verification, the file is fully protected against unauthorized access and tampering. This unlock action function is used to decrypt a file when the user selects the unlock option. First, we check is locked to see if the file is actually encrypted. If it's not locked, we update the status label and show a warning with messagebox.showWarning, then stop execution. Next, we ask the user for the password using simpleDialog.askString, hiding the input for security. If no password is provided, we simply return to avoid attempting decryption. We then call decrypt file path and password, which tries to decrypt the file and returns a success flag and a message. If the decryption is successful, we update the status label and show a success pop-up with messagebox.showInfo. If it fails, we update the label and show an error message using messagebox.showError, letting the user know the password was incorrect or the file is corrupted. This decrypt file function is responsible for securely unlocking a file with the provided password. It first checks if the file has exceeded the allowed number of failed attempts and enforces a lockout period to prevent brute force attacks. Then, it opens the file and verifies it contains the binary locked marker, ensuring only encrypted files are processed. It reads the salt, IV, HMAC tag, and ciphertext from the file to recreate the encryption key and verify the data. We derive the AES key and a separate HMAC key using pbkdf2, which ensures the password is stretched for strong security. The function recalculates the HMAC tag and compares it to the strong tag to detect any tampering or corruption. If the HMAC fails, an exception is raised to safely stop the decryption process. Next, we create the AES cipher with the key and IV and decrypt the ciphertext, removing padding with unpad. The decrypted content is written back to the file, effectively restoring the original data. Any previous failed attempts for this file are cleared since the decryption was successful. If an exception occurs, the function records a failed attempt, updating the count and timestamp in failed attempts, and returns an error message. This prevents repeated incorrect password attempts from compromising security. By combining AES decryption with HMAC verification and attempt tracking, the function ensures files are decrypted safely and only by authorized users. And that's the whole thing. AES 256 encryption, HMAC tamper detection, PBKDF2 key derivation, brute force lockout, master password protection, and a drag and drop UI. All in about 150 lines of code. The key takeaway here, encryption done right isn't just one thing, it's layers. Random salt so every encryption is unique, separate keys for encryption and verification, slow key derivation to kill brute force, HMAC to detect tampering. That's what makes this actually secure, not just pretend secure. Drop this code, run it, and your files are protected with the same fundamentals used in real security software.